I want to touch on what I was talking about at the end of the last video really quick to make sure that we understand this. But when this mass is moving through the equilibrium point, it's not experiencing any restoring force because the restoring force is trying to get it back to equilibrium. So if it's already there, there's no force. However, force has been added to it all the way until it reaches that point. So it has been accelerating that whole way. And so it has its maximum velocity as it passes through equilibrium. Once it passes through equilibrium, it's going to slow down because the spring is now compressing and a new restoring force is going to try and push it back towards equilibrium. When the mass is at its farthest distance, the restoring force is going to be the maximum. The restoring force has to deal with the distance. So if the distance is maximum, so is the force. And then the velocity is going to be 0 for just a second. For a moment, this mass is not going to be moving. It's going to switch from going to the right to stopping to then turning to the left. But it's going to be accelerating the most in this moment because we know that force equals mass times acceleration. So if mass or if force is maximum at this point, our acceleration is also going to be at maximum. Same idea applies to our pendulum here. So it's going to be moving the fastest through this equilibrium point, which is where the ball and the string is just hanging straight down. And then this distance here is going to be the farthest distance, but instead of distance in meters, we're going to be talking about distance in the angle between the equilibrium line and where the position of the pendulum is. So what does the period depend on for either a mass on a spring or a pendulum? Meaning, how do I make it so a wave, or how do I make it so the mass on the spring goes faster? Or how do I make a pendulum swing faster? To do that, the only two things that are going to change the period for a mass on a spring is going to be the mass itself, or it's going to be the spring constant, how sturdy or how stiff the spring is that the mass is attached to. For a pendulum, the only thing that changes the period is going to be the length of the string or gravity. Seeing as gravity doesn't change on Earth, it's just going to be the length of the spring or the length of the string. That's interesting because it means that whether you put 100 kilograms onto a pendulum, or if you have a pendulum that's 1 kilogram, if they have the same length string or length of the rod going to the top, they're going to have the same period. They're going to be swinging at the same speed. So to graph an oscillator, something that's moving back and forth, it is best to do it graphing it over time. So it's going to be moving from one end to the other, to the other, to the other. If we just drew that, we would just draw a line back and forth, back and forth. So instead, we're going to measure its displacement over time. So on the y-axis, we have its displacement in meters. This could be horizontal displacement or vertical displacement. And then for our x-axis, we have time. So our wavelength, it's not going to be wavelength, it's going to be the period is measured from our crest to our next crest. So let's talk about the equations for simple harmonic motion. This is what they look like if you were to just write them out, but if you were going to put them into a calculator, you would put it in just like this. So angular velocity we haven't really talked about, but what it is it's 2 pi over the period. That's the same thing as our angular velocity. The only thing you really need to know about this is that it goes into our wave equation. So our wave equation is x of t, so the displacement at a certain time is going to be equal to the amplitude times cosine of 2 pi over the period times t for time. Okay, A is for amplitude, T is for the period, or capital T is for period, little t is for time. The only thing that changes between these two equations is this one has cosine and this one has sine. We're going to learn when to use each one of those in the next video.